The problem statement from GATE Physics 2022 paper reads as follows. For the op-amp circuit shown below, choose the correct output waveform corresponding to the input Vin equal to 1.5 sine 20 pi t. The unit said volts. The saturation voltage for this circuit is plus minus 10 volts. So as it's clear, Vin is given and we need to find out the output waveform. But before we start to solve this problem, we'll visit some questions. We'll ask ourselves some questions. First, is this an ideal op-amp? Now, the question is silent about it. The question says just op-amp circuit. So if nothing is said in the question, we'll assume that it is an ideal op-amp. Second, is there a feedback in this circuit? How do we check if there is a feedback? Whether the output node is talking to any of the input nodes. So output node is being fed back to this non-inverting terminal through this feedback resistor of 20k. So feedback, yes, there is a feedback. Now, what kind of feedback? So we can see that the output is connected to non-inverting terminal, the positive terminal. Hence, this is a positive feedback. Okay. Now we have done all that. Okay, one more thing. Since this is an ideal op-amp, we'll assume that the current flowing into the inputs is 0. Right. So I'll write this same thing here. So current going in here is 0. Now let me change the pen. We are going to talk about an interesting concept here. Remember that there was an R in here. The input impedance, right? So what I'm going to do, I'm going to write Ohm's law across this input impedance. So I can write V plus minus V minus equal to I times Rn. Usually Rn is a very high number, mega ohms or something, and since current is 0, so I get V plus minus V minus is equal to 0. This implies V plus equal to V minus. Now this specific condition is referred to as virtual short. Why short? Because both of these are the same potential, as if they are shorted, but it's a virtual. They're actually not shorted. It's called a virtual short. But effectively this means is that this potential is the same as this potential. So we denote it by a dotted line like this. This dotted line denotes that these two nodes are virtually shorted. They are the same potential. Right. Now let's try to solve this problem. Let me change my pen. Excuse me. Yeah. So input, we are given an input voltage and some saturation voltage. We need to find V out. So let's assume that value of this node is Vx. Now we know this is the virtual short condition. So V plus is Vx and V minus is Vin. So we got this value. Vx is equal to Vin. Let's label this as equation 1. Now let's try to find out. Okay, let's assume that a current I is flowing through here. The same current I will have to flow through here. Remember, if we apply a KCL here, since no current is flowing through this arm, all the current that is flowing through 20 kilo ohm resistor must flow through 2.2 kilo ohm resistor, because there's no way the current can go anywhere else. Correct? Now let's apply Ohm's law across the 2.2 kilo ohms resistor. So I'll write here Ohm's law across 2.2k. So I'll write the potential drop, that is Vx minus 0, equal to current flowing is I, the resistor value is 2.2k. So I'll get I equal to Vx upon 2.2k. Let's call this expression 2. I'll also write Ohm's law across the 20 kilo ohm resistor. So Ohm's law across 20k. We write the voltage drop, that is V out minus Vx, is equal to current flowing through this is I times the resistor is 20k. So I get the value of I equal to V out minus Vx over 20k. What I'm going to do is since we found the value of expression for I in both these scenarios, I'm simply going to equate. So I'll get Vx upon 2.2k equal to V out minus Vx upon 20k. And now just cross multiplying, so I'll get V out equal to Vx 1 plus 20k upon 2.2k. Now so I'll just calculate these values. So that is 20 over 2.2 is 9.09 plus 1, so that will be 10.09, right? So V out is nothing but I'll approximate it as 10 times Vx, and Vx is nothing but V in, so I can write it as 10 times V in, which is equal to, now the value of V in is 1.5 sine omega t, so I'll put this value of V in here. Now remember that omega is some I think it was 20 pi, so it's irrelevant here, it doesn't it's not playing any role, but just for the sake of completion I'm writing this. So 10 times, so that will be 15 sine omega t. Okay, now so we have found the expression for V out as 15 sine omega t. Let's go back now. So the input is sine omega 1.5 sine omega t. Okay, so let me draw the input here. So this is the input, correct, and we'll have our output here. I'm using a different colored pen for this, right? So that is 15 sine omega t. Okay, they are in phase, remember that. So let's see, so this is V out, and remember that this is V in, and obviously the x-axis is time, this is time axis, right? So we see that so this cannot be an option B is eliminated, because okay, now remember that saturation voltage plus minus 10 volts. So what's going to happen that this, remember the peak is 15 volts, so this is never going to reach the 15 volts, is never going to, it's going to be saturated at 10 volts itself. So it's going to be cut off, so this will be a bit clipped, so actually it will look something like this. I'm redrawing this here, so it will go up flat, come down flat, like this. So it has to be something like this, the output waveform. Why is this clipped and this is clipped at 10 volts and minus 10 volts? Why is this happening? Because the output voltage cannot go below the saturation voltage, which is plus 10 volts and minus 10 volts. So D cannot be an option because there's no oscillation here. C cannot be an option because it has to be clipped. See, remember, it has to be clipped. So C is eliminated, B is obviously eliminated. So the most correct choice that we have is A. Now remember that there has to be some sinusoidal component here, which is not very prominently visible here. Okay, but the closest that we can get is this. And remember, in theory we have talked about that since there is a positive feedback between an oscillator, right? So these were the two options, but the closest one is this. So we'll go with option A, the square wave that we are getting. Okay. Thank you for listening.